Hello, everyone. This is lecture 10 of Petroleum Reservoir Geomechanics 465531. Today, we should finish Module 1, and if there is time left, we will proceed with the start of Module 2. But before we finish, I want to reiterate on some important stuff that we covered last lecture, because maybe it's a 1 hour lecture now. Maybe I went through it a little bit faster than what I wanted to. And I want to make sure that everybody in the class, all 7 students that are enrolled in this class, understand that concept. Some of the concepts that I went through last time, and as you understand, these are very important concepts. It's the most important concept takeaway from applied takeaway from this class, actually, that we went through last time. Then we have a minor subtopic to discuss, and then we're done with module 1, and then we are starting module 2, which is a big module in this class as well. In fact, they say is from feedback that I got from students last year, module 2 was the toughest one and the most sort of dry mathematical one, but things are gonna get better. Just like I said at the beginning of the class, that we went through a little bit some complicated math, and then things became a little bit easier with the Andersonian faulting theory. Similarly with module 2, we get a little bit complicated and then things start getting easier. Anyway, so let's start. Last time we did talk about fracture, how to fracture tensile mode 1 fractures initially. And we know there is 3 modes of fracture, right? Mode 1 is tensile. This is like taking chopsticks of a Chinese restaurant, and you flip them over and you pick up the legs of the chopstick and you put them apart. This is a tensile fracture, a mode 1 fracture. And this is what we are discussing. There is also mode 2, which is shear in plane, and mode 3, which is shear out of plane. I told you about how those are, but we are not going to go in depth in those until later on. So now, this is really a topic from module 3 that I moved to module 1 last year because I found it very fundamental. It's dependent on the in situ stresses, which is what we cover in this module. So I moved it like earlier on. Anyway, so for mode 1 fractures, think of a page, okay, a page from a book. This is a mode 1 fracture, okay, a tensile fracture. When I see a tensile fracture, I would use a direction to characterize, to indicate the way it opens, and that has to do with the width of the page. In what direction does that open? That would be, I would say, the direction of a stress. And that would be the direction of the least compressive in situ stress, S3. And then for the propagation, I'm not going to indicate the propagation with a direction. I'm going to indicate the propagation with a plane. Okay? The fractures propagate in a plane made by the other 2 stresses, S1 and S2. You need 2 directions to indicate a plane, okay? So I'm going to say they propagate in a plane of S1 and S2. So I want a direction S1 and S2, or S1 and S2. Same thing. I can be more laconic and say they open in the direction of S3 and they propagate perpendicularly or orthogonally in a plane orthogonal or perpendicular or normal to S3, okay? That is, okay, they open in a plane, they open against S3, so they open in the direction of S3. But a plane perpendicular or normal or orthogonal to S3 is made up by the other two stresses that are at right angles to S3. So I'm basically saying the same thing. I wish I could draw. I don't see a marker. But, well, I don't need to draw on it. What am I saying? Okay. So I can draw on the screen. Okay. We said that the stresses, oh, sorry. The stresses are mutually orthogonal. So if we have S1, S2, and S3, the certain thing that we have is that they are orthogonal to each other. So if I say, okay, the fracture opens in a direction of S3, that means, where is the direction of S3 is in this way. So the fracture will be opening somewhere like this, the width of the fracture. I hope I draw it correctly. No, I didn't. No, that would be a tough one to draw, but okay. The width of the fracture is perpendicular, is in the direction, not perpendicular, along S3. And then I have the plane at which the fracture propagates. Okay, clearly, this is the width of the fracture. This needs to be in the direction of S3. But the way the fracture grows is perpendicular to that. So it would be a plane orthogonal to S3. And to be more precise, it's a plane bounded by S1 and S2. So this is the plane at which the fracture propagates. A plane is basically a flat surface, a page, if you will, something like that. So there are many ways. It can be confusing at the beginning. That's why I'm going over it a second time. But when you see a fracture, I would say, let's put a protocol, like a series of steps, short steps, nothing crazy. That, okay, I see a fracture, it looks a tensile fracture, it looks like a page. Okay, and I want to decide what it tells me about the stresses. So I will make, first step, I will see, find the direction, sorry for my handwriting, the fracture is opening against. Okay, that means width of fracture. Okay, where is the fracture width? Is in this direction. Okay, that would be S3. I found S3. Then I'm dealing with the other two. So I'm dealing with the length and the height of the fracture, which is what makes the plane the flat surface. Okay, we said last time, one of them is stronger than stress than the other, and the one that is the strongest stress is not going to let the fracture grow as much in that direction.
Yeah.
Exactly, or height.
Or height, sorry.
Yeah, it depends.
Length most of the time is SH, S2.
Well, it can be.
The length most of the
Well, if it's strike slip, if it's normal faulting,
normal faulting.
yeah, if it's strike slip, the height would be very short, right? Yeah, it would be the other way around. Yeah, I guess you have more normal than strike slip, so it makes sense. Now, step number 2, we should call it, I don't know, protocol for mode 1 cracks. Also known as tensile fractures are also known as opening mode fractures. That means you're really looking for how they open. That's the most important thing. So number 2 is check propagation plane, check which of the directions, check length and width, and height. Okay. Smaller of the two, smaller is basically, smaller is gonna be the S1, bigger of the two is gonna be the S2, right? Okay. So out of those, or not check, compare. I think compare would make more sense. Compare length and height. And the smaller of the two is gonna be S1, bigger of the two is gonna be S2. Length and height, compare length and height along the fractures propagation plane. Okay. So that's, I know it's confusing. It can be confusing when the first time you're dealing with it. 2 steps. Very nice. Think about it a little bit, and if you have any questions, shoot me an email or the TA. He will explain them to you. When it comes to application in the field, this is why we drill our wells parallel to SH mean. But that doesn't mean that always drilling your wells parallel to SH mean you will get a fracture that is what you like, transverse to the wellbore. It might be that you have a reverse faulting stress state and you get longitudinal. So drilling the well against SH mean is not good enough to get you a fracture that is how you like it to be. What I was gonna say, I forgot.
Field application.
Yeah, field application. Yeah. Thank you. Also, you don't know it right now, but we're gonna learn later. Having a wellbore there impacts the stress field around it. It doesn't mean that if SH mean is the direction of the least compressive, SH mean is the direction of the least compressive stress, S3, in normal and strike slip faulting, assuming there is nothing else there interfering. Okay, I put the well, I remove rock, it means that I remove rock and I fill it with fluid, replace that rock with fluid. Things are changing, it impacts the stress field in ways we are gonna see later in this class. So things are changing, and then if you have perforations, things change even more. You are introducing perturbations, as we call it, to the stresses, yeah, near the in that vicinity, yeah, exactly, yeah, exactly, and it can mess up the situation. So that's why I wanted to go over it one more time today to make sure that you guys are. I want you to make yourselves comfortable with it, in particular the undergrads, because the graduates might have seen it before. Undergrads might be the first time, and you're gonna see it again in well completions, and you will see it again in this class. But yeah, this is mode 1 fractures. And it was intentional last year that I moved this subtopic from module 3 to module 1 because it's so important how the fractures open. So important to what we do these days. Okay. The problem, I don't think there is any questions in the example problem number 6 we did last time. We tried to put some application sort of aura into this problem, and we looked into a problem in Fort Worth, Texas. I didn't get any questions on it by email, so it should be okay. I get it all in class. The students who are in class were fine with what we talked about. And the last subtopic of this module is basically gonna be estimating S3. Okay, and that is a little bit more involved than estimating the overburden. And it says estimating S3, it doesn't say estimating SH mean. But most of the time, this technique is used for estimating SH mean, which is S3 normal and strike slip faulting. Now, it involves a little bit more of a human action to do that than with overburden estimations, which is basically adding up the weight of the earth above you. And for that, we will do we will be doing about leak of testing, and I want to make sure that I have the right plot. If you see in your slides, there is nothing written because I was planning to draw something, and I want to see from my notes that I draw it correctly. I don't want to make a mistake. Okay. So when we drill a well, we stop and we run casing, we cement that, and then we carry on drilling deeper and deeper and deeper, and then we stop again, we run. Before we start, every time we start drilling, we do a kind of test that is known as the leak-off test, and it has several variations of it. They are basically, Dr. Espinoza from Texas, he calls it hydraulic fracture test. Extended leak-off, mini-frac, all those, that family of tests. Okay, I will go one step more general, and I will call it tensile fracture test. Okay, they all do the same thing. They get to the point where you start injecting or you start pressurizing your wellbore in different ways. But there are several ways possible you can do that. But the goal is to get the well to the point where a tensile fracture is just about to start. Okay? And then when the tensile fracture starts, it gives me, I do something, I stop pumping, and from the way the pressure behaves, I get an indication of what is my S3. And why I am measuring the S3 is because the tensile fracture will open against S3. It needs energy sufficient to start opening against S3. And then I know, okay, this is the energy needed to open against S3. So my S3 value in this location, in this depth, is gonna be this X amount of that I'm calculating. By the way, Dr. Lundstern agreed to present to us. It's gonna be a Thursday, I think. I don't know if it's next Thursday or the Thursday after, but he's gonna give us a presentation. He's the guy with the colorful maps from USGS. And somebody was asking me, I think it was Justin, what depth he was looking at. Like that maps, they are not all at the same depth. It's depth from where he has data from. Like leak of testing data is something that he used as well. And I bet if you ask him, he's gonna talk about those. He is very good presenter and very nice slides. And I believe Dr. Schultz, our chair, was in his PhD committee. So there's a good chance that our chair will attend as well. Because I remember when I was in Texas, Dr. Schultz showed us Lundstern's, he was Lund's knee by then. He showed that his proposal that he wrote for Stanford, because it was very, very good. Very, very good. Like very, very, he was excellent, like very, very good. Anyway, so let's see. Okay. I have a well. Oops. Sorry for going slow. I'm going slow because I don't want to. I will go it here. Okay. I fill it up with. I'm going slow because this is an important topic. I fill it up with mud. And I'm just about to. I want to start drilling further. I changed my mud weight, blah, blah, blah. And I'm just increasing the pressure. So, huh? Yeah, but I'm also pumping now.
Yeah.
I'm pumping without drilling.
Oh, okay.
Yeah. I'm pumping without drilling and I'm raising the pressure. Yep. The pressure exerted by mud at that exposed location, which is directly below the casing shoe depth. Undergrads who take this class already took advanced drilling, so you guys know about the casing shoe depth being the weakest point. Like if my casing stops here, the shallowest point I can have a fracture is right below it, because deeper and deeper I need more stress to do that fracture. Okay, so I have time on the horizontal axis, pressure. Yeah, pressure on the. Let's see. I will write pressure then, so I avoid confusion. And then time. I will write time here. Okay. And now we are starting to pump. Yeah, we are pumping mud. We have the pore pressure of the rock. We are a little bit above that, okay? We are calling it overbalance, because if we are below that, we have fluids coming into the hole. We're gonna have a blowout if we don't, we are not serious. Okay. And then, huh?
You're increasing pressure.
Yeah, I'm increasing the pressure. Look at how I'm going up. It's fairly a constant gradient, okay? As constant as my hand can make it. Okay, and then I reach a point where my slope is starting to deviate. What does that mean? Now that my slope is going down, is decreasing.
You're pushing inside the formation.
Yeah. My fluid is leaking into the formation, so the pressure is not rising as fast as it should have rose if it wasn't going into. We call this the leak of pressure, LOP. Okay, the leak of pressure, LOP. And now say I'm not in this situation, or I am, I'm an amateur. I'm a brand new guy. I didn't notice the leak of pressure, and I keep on pumping. Okay, I didn't see it. I say keep on pumping. What is going to happen is that the pressure will keep rising at this diminishing pressure increases. So I'm getting pressure increase that is smaller than the amount of fluid I'm pumping, because I'm losing the fluid to the formation. And then I will hit a point where my pressure will drop abruptly.
Is structure.
Yeah. We call this the formation breakdown pressure. FBP, formation breakdown pressure. And then what is gonna happen is if I keep on pumping, okay? I didn't notice this. I keep on pumping. I'm not good at my job. I keep on pumping. It goes a little bit straight. Yeah, we call that the fracture propagation pressure. Now I realize I made a mistake, okay? I stopped pumping. Immediately, my pressure dropped like as soon as I stopped pumping, okay? I really stopped pumping immediately. My pressure dropped to this level here. We call that the ISIP, instantaneous shut-in pressure. And then I stop pumping. So my pressure will go like this. It will level off to what is known as FCP, fracture closure pressure. Now, I want you to look at that. Yeah. And I want to redraw this part. I want to make it a smoother curve. It's very hard to learn these pens that they have here. It sort of levels off. This one kings upwards, it shouldn't king upwards, but anyway. Best I can do. Now, I want to draw something here. Okay, from leak of pressure until FBP, until the breakdown pressure. In that pressure range, I can have fractures initiating, tensile fractures initiating, mode 1 fractures initiating. As low as LOP, as high as FBP. Obviously, it won't go as higher than FBP because it was a natural reaction that went down like that. Okay? Now, if I was good at my job, what I will do, my leak of testing, would be like this. I started here, I'm going up, going up, going up. I get to leak off. Now I notice leak off. I go a little bit further. And then, hey, Hakim. And then I stop pumping, okay? I stop pumping immediately. So as soon as I stop pumping, I get this drop that is basically to the ISIP. And then I level off. Sorry. And then I level off. I didn't do it very correctly, but I level off to FCP. Okay. All right. And then I basically stop pumping. I go back to where I was. If I remove the fluid, I can go the extra fluid I pumped to bring the pressure back to where I was, port pressure, to be back to balanced conditions, basically. But I don't care about the last line now. I care about this because this is my standard leak of test. The red line is the standard leak of test. I pumped, I went up to leak off, I noticed that it's there. I went a little bit further. I stopped pumping. I measured the ISIP and the FCP. So these three values that I got, LOP, ISIP, FCP, it doesn't look very well from the graph, but they are very close to each other, okay? They are very close to each other. And because they are very close to each other, there is people who say LOP is basically S3, a good approximation for S3. There is people who say FCP is the good approximation for S3. There is people who say ISIP is a good approximation for for S3. There is people who say that use the tangential method. So come here at this ISIP, draw a tangent, then come at FCP, draw a tangent. Where those tangents meet, this is S3. There is a lot of controversy. There is people being very, very against, like Mark McClure of ResFrag is very against using the tangential method because he says it gives you very, very high values for S3. For this class, just like we did in drilling, I will say, let's go with the highest point to have an overestimation of S3. And I will go with the ISIP.
Leak-off pressure, is it the same as ISIP?
It will be very close, not exactly the same. A lot of things don't depend on rate. You can use another rate, higher, everything would be higher. So it can be very, it can vary a lot.
Depends on the materials where
Yeah.
elasticity and stuff like that.
Yeah. But the material is intrinsic property of the rock. So the mat that you are using, is it heavier? What rate are you using? Rate will affect FBP a lot as well.
Yeah. For example, FBP is the initiation of the breakdown.
Yeah, initiation can happen at any point from leak-off to FBP.
That's the problem of rate. If
Yeah.
you're gonna add rate, you will have.
And the rate will affect leak-off and breakdown, but it will affect breakdown more than leak-off. So it will make it sort of expand the window. It's very sort of test specific. So if you run one test, you have a set of results, you analyze it a certain way, you get some values. You run another test, you get a different set of results. You know, it's very how to say, real world kind of. A lot of things vary. For this class, I will say ISIP. I prefer to use this for your approximation for S3. Let's just say that S3 is approximated by ISIP, but I wouldn't like, how do you call it? I wouldn't put, how do you say, throw myself in the sea for it or something like. It's a good approximation. Huh? If you want a bigger value, basically. If you want a smaller value, maybe you go with FCP. I have seen people using any of those three as approximations. And of course, there is a lot of research.
So don't use leak-off pressure.
You can use leak-off, but I'm saying for this class, yeah. You may have only one data point on leak-off pressure. Somebody told you leak-off pressure, then you use leak-off, and you don't have anything else. And leak-off is not very far from ISIP, right?
Yes.
It's not very far, so you're not deviating much. I would say case by case basis, like if you want a low value for a maximum limit, okay, use FCP. If you have FCP, I don't know.
So is it best to underestimate S3 or to overestimate?
It depends on your function, right? If you are building a mud window, you want to underestimate, right? So you are gonna go with a lower value in that case, right?
For fracture pressure?
Yeah, because you want the lowest possible fracture pressure that you have to be on the safe side, right? But if you are doing it from a hydraulic fracturing perspective, and you want to estimate how many tanks you need to have there, pumps you need to have there, sorry, and how much horsepower do you want, because a hydraulic fracture job will try to initiate multiple tensile fractures. Okay. I want the highest value. I want to overestimate the horsepower that I need to bring enough pumps in the place. I don't want to go under. So speaking of which, I have here, there was, Fervo, the geothermal project,
Use the company.
Fervo Forge project. Fervo is involved, no, the Forge, Forge.
Utah.
Huh?
Utah.
Yeah, in Utah. I have heard from somebody working with that there was a stage that didn't even make it to breakdown pressure. They pumped as high pressure as they could, but they didn't they didn't get breakdown. So these things are possible. Of course, it's a harder rock. I think it's a mix between igneous and sedimentary. I would say in that case,
We have a formation in Algeria, they pumped 15,000 PSI and couldn't even.
Oh wow.
Yeah.
But it's very deep.
Yeah.
So it has natural fractures. So that's why they use MPE to keep the natural fractures open.
Oh.
Otherwise, you're gonna compromise your reservoir.
Yeah. I would say in that case, if it's possible, and we have to do it again, we pump slower at a slower rate.
It will extend, I guess.
No, to pump at a slower rate, so it brings everything down.
Yeah, but it will take time to reach break. And you will have the road who will be familiar with the pressures.
If it reaches breakdown, it might not even reach breakdown.
So usually when they fracture, they close the BOP to fracture, everything close, or what they do?
BOP to fracture?
Yes. When you start pumping.
Oh, there is no BOP, there is something else they are called the monoline, which is if the pumps are connected to the monoline and fluid flows from there down hole. There is a frac tree.
How about the return flow?
There is no return flow.
They are pumping like.
Yeah.
So you pump there, but you have a return.
The return is a different job, it's a flow back. You need to bring a different company to do the flow back. But you have a frac tree on top of the well, on the wellhead, when you do a fracture job.
So you pump from the annular space, or you pump from?
No, from inside, yeah.
From the pipe.
Well, it depends on what you pump into empty casing most of the time.
So if you pump inside, you have a return in the annular space.
No, everything goes downstairs and wants to go into the fractures. And then you are gonna pump proppant. You pump pad first, which is
They
basically,
use a pocket.
yeah.
The interval that they.
Yeah, you
Okay,
have
so they
a,
close the pocket of the return. That's why we don't have.
There is no
return.
return.
there is no return until you have flowback. The flowback people, it's gonna be a different company that will come to do the flowback. It would be, the flowback will do this. Look at the turquoise line, the blue line. Okay, we're at FCP, and the flowback people will do this.
So they open basically and they don't pump.
Yeah, they pump out the fluid. They try to pump out the fluid without removing the prop.
So they just open the flow line, that's it.
Yeah, they pull the water back or the fluid back.
With like vacuum pumps or something?
It's a different,
Do they have a
different
specific
process, yeah. And they do it slowly so that you don't move the fluid,
The propan.
the propan out. Yeah, you don't want to move the propan. I knew a lady, her husband was working for flowbacks here in Williston. Yeah, I mean, it was, it's a separate company doing flowbacks.
It doesn't have to do with oxidizing or something like that.
No, if you want to do fracturing with acid, you need to design a job that is fracturing with acid. And then you basically are doing matrix acidization at a higher pressure than the breakdown.
So do they have a drill pipe to go and pump, or they pump through the annular space?
Well, you have a liner along the lateral most of the time.
Oh, okay, so you're producing so you're pumping the casing.
Yeah,
why there is no return.
yeah.
There is no pipe inside the pipe.
There would be a return eventually.
After.
Yeah, but there is no circulation.
There is no circulation.
No circulation. It's like, okay, it's like continuous mud cap. It goes only one way. It doesn't come back.
Yeah, one-way valve.
Yeah, but continuity is like, because we have open fractures already.
Yeah.
There is a piping.
Okay, yeah,
But
you
this one
lose
is
it.
like, you don't have your, you are killing the well through the choke, and you don't have a pipe.
Yeah, but the fluid that you are pumping down, once the fractures open, it will go there.
Yes.
So it needs to occupy this volume outside the well, right? The fracture will go, and then they need to keep them open until the proppant goes through and stays there. And then you want to remove the pressure, make sure the proppant keeps the fractures open. You don't want to do it fast because you want the fractures to stay open, and then you want to do the flow back smoothly.
So they pump the proppant from the surface all down.
Yeah,
It doesn't stick in the casing, like.
it can.
They calculate time of gel freezing, something like that.
Yeah, there's a lot of stuff you can do. We see those in the next class, like several techniques.
Completion?
Yeah. There is a plug and perf. There is a ball activated.
Because I remember one time I was in the field, so there were frac operation there. One guy, he was like testing the time of the fluid viscosity. He
Oh,
was steering in with the steer and
Uh-huh.
calculate the time at
Yeah,
which
yeah.
time it's gonna change.
gelation, yeah.
Yeah, gelation stuff.
And you have also the people with when I was a young student and I went to my first ATCE on 2012 in San Antonio. Something happened in that ATCE. Don't remember. It was when the ball activated technique came by and they were like, these balls are made by material that will dissolve in these conditions or after this time. They knew there are some that dissolve. You can make them at the downhole conditions to take like 10 minutes to dissolve or something, or like half an hour. That means you have half an hour to do something, It gives you, they need to plan it. Or you can go with a coil tubing activated. You can do coil tubing with a sliding packet. And you go with the coil tubing, you go to the interval that you want to fracture, you have a packet, it isolates everything before it does the job, so you have a pressurized section of the well, but it doesn't affect what is behind it. And then you fracture there, you release the packet, you come back with the coil tubing, you activate the packet, and you go until you,
Stage by stage,
yeah. And also the pressure that you are gonna reach, there are techniques that don't work in high pressure environment. You need to take care of all this. But for now, the only thing that you need to know is that leak-off testing is used to indicate an approximation for S3. And this is how leak-off testing works. Now, quick question, since we have 5 minutes. Say I didn't do the flow back, as I showed, and I go back. I want to go back also here. Oops. Okay, see the turquoise line? And let's just say that I make it better. Like this, and then FCP, I guess, but I keep on going down. Okay, if I start pumping again, how high I will go until I get my next FBP? Less. Why?
Because you already have a fracture.
Okay, yeah. The fracture closed, and now I'm trying to reopen it,
Maybe.
but the rock is already broken.
Yeah.
Right?
Yeah, the rock is already,
Yeah.
so you're just gonna move, like, play with the width, with the aperture.
Yeah. So
Like the rock has been weakened before.
it's already broken. So it's like moving, you don't need to break the rock again.
Yeah, exactly.
Yeah. How do you break the rock? when you do those fractures?
How to?
How do you break the rock?
It's like,
What kind of fractures are those?
Tensile.
Yeah.
Yeah, tensile mode one.
So you already broke the rock, and then you remove the fluid, it closed, and now I'm trying to open the rock. I'm trying to open an already existing fracture, is what he was saying, natural fracture.
Oh, The thing is, if you're gonna repump, is it gonna be like, gonna reach the FCP, the closure pressure?
I don't know, that
At the same
depends.
rate?
That depends, let me see. I
there is
mean,
no rate on FCP.
well, it's
Not
not pumping, but he's asking, it should be close, I would say. But I wouldn't guarantee it would be the same. And you know the difference on the crest.
Yeah.
What is it? What would be the difference of the first crest with the second one? Okay, if my second FBP is like here, what is the difference with the first crest? We're gonna learn about it. FBP2, FBP1 and FBP2. What is the difference between those? I just want you,
Fracture initiation.
yeah, no, related to that?
So-
You don't, huh?
FOP.
Huh?
Pressure.
ISIP.
No, the difference is actually the tensile stress of the rock, strength of the rock, which we are gonna talk about later on in class. But
Yeah.
is the tensile
It's,
strength of the rock. Yeah,
So it means you roast it?
huh?
It means once it.
It's what you need to break the rock. Okay, that's one way of getting a field indication of the tensile strength of the rock. But
So when
you don't need to know that at this stage of the class. We are gonna learn it later on because we are gonna talk about tensile fractures.
So the curve that you have from LOP to FVP, is it the same that you will have from SIIP to FCP?
No, no, you are talking about this and this?
Yeah,
No, they are not the same.
like the reverse. No.
They are not the same. My old professor in geomechanics, John, also was saying always that ISIP is immediately. I stop pumping and I measure the rate. It goes like flat down and then it stops at a point. That's the ISIP. And then if you keep it not pumping, it levels off.
And it's stabilized.
Yeah, sort of. But it will still go down. But it levels off and then keeps going down again. Like, yeah. So,
Depends also on the,
yeah. But league of testing,
You
okay.
can determine as well, like, after stopping pumping, you can determine like the aperture of your fracture from that.
Yeah, there is a lot more complicated tests that you can do, like extended league off,
Yeah.
mini frag,
They give
etc.
you basically the permeability of your, like, hydraulic fracture.
Yeah, we do a lot of those in the next class.
Okay.
In advanced stimulation techniques, we do a lot about those. But the main thing of those family of tests, what Espinosa calls hydraulic fracture test, let's just call it tensile fracture test, is basically to get to the point where I'm just about to open a tensile fracture, I'm leaking off, maybe I have opened it, maybe I haven't, but then I want to stop pumping and understand my S3. Like get an idea of where my S3 is. Okay. And we said in this class, let's use ISIP for S3 approximation, even though it's controversial. Anything I say, if I say use a LOP, it would be controversial. If I say use ISIP, it's controversial. If I say use FCP, it's controversial. If I say use the tangential method, Mark McClure would be sending an email complaining. You know, it's like everything is, anyway. Anyway, that's how we finished module 1. What did we learn? We learned a little bit about structural geology. We learned about subsurface stresses and principal stresses. We talk about Andersonian faulting theory. We did overburden estimations. And I hope none of you get into this subdiscipline in the future because it doesn't pay very well. Talk about pore pressure, overpressure, underpressure. And finally, we talked about the orientation of tensile mode 1 fracture growth. In general, if we have this REV, we talk about stresses acting, external stresses acting on that REV, right? We talk about SV, SH max, SH min, or S1, S2, S3. We talked about pore pressure from inside. Yes, it's inside, but it's acting from a fluid that is not basically the rock, right? Everything from outside, like in situ stresses, in subsurface stress state. In the next module, we are going to be talking about how the REV behaves in terms of stress applied to it and strains induced, or strains applied to it and stresses induced. It's going to be a very mathematical module talking about how does stress relates to deformation. So far in this module, we have seen what we call computational people will know boundary conditions, like SV, SH max, SH min, and this kind of stuff. Next module, we'll be talking about what people call constitutive modeling, constitutive relationships, which is, okay, I have this stress, I'm getting this deformation. I have this deformation, I'm getting this stress.
Because of this.
Yeah, it's more stuff that go within the REV. We are going to see some people like Cauchy, Lamé, and one more, Voigt. Some more, I don't know that. We're going to see matrices and some like differential stuff. And yeah, students don't like this module 2. And I didn't like this part of the geomechanics also when I took it. But becoming a graduate student, I had to use this stuff. So I would say be patient with it. They will become easier. Yeah. And homework 1 is due on Monday, 1 minute before midnight. Yeah, make sure that you don't submit it late. And I will see you all on Monday during the lecture time. And we'll start fresh module 2 then. There's no point in starting it now. Thank you very much. Have a nice weekend.